Hi, my name is Shahnawaz. In this lecture, we'll introduce the free abelian groups. Let us begin this lecture with the following observation. So, this is the observation. So, let us consider a group G. Let G be an abelian group. And M be any integer. Let us write the set MG to be the set which contain elements of the form MA, where this A is in G. We claim that this is a subgroup. So we claim that this MG is a subgroup of G, and hence a normal subgroup of G, because G is abelian. For if we consider two elements, say X and Y in MG, then this X is M times A and Y is M times B for some A and B in G. Now if this difference is in G, MG, then if we prove that X minus Y is in MG, then indeed MG is a subgroup of G. Now X minus Y is MA minus MB. Now G being abelian, we have this is M times A minus B. Since A is in G, B is in G, so their difference is in G because G is a group. So this is an element of G. So this whole thing over here, this is an element in MG by definition of MG. Hence MG is a subgroup of G. Now let us prove the following proposition. If G is an abelian group, then we know that let G be an abelian group. And suppose P is some prime number and P is a prime number, then we claim that, then we have to prove that then G mod PG. Note that this PG is a subgroup of G, hence a normal subgroup of G, as we have already proved MG is a subgroup of G. So we claim that this G mod PG has a vector space structure over, then G mod PG is a vector space over Z mod pz, where the Z mod pz is a field of a finite field. So to prove it is a field, we just only need to prove the vector space axioms. Obviously G mod PG is an abelian group, so we have to prove the other axioms which are related to the scalar multiplication. Now let us define first here the scalar multiplication. Let us prove this. Let us consider an element, let R bar belongs to Z mod PZ. R bar means it is actually the coset R plus PZ by definition of Z mod PZ. Let R bar belongs to Z mod PZ and A belongs to G. So let us define the external multiplication, which takes an element in the field and let and A belongs to G. Then define the scalar multiplication. Define the scalar multiplication. That is ruled by this dot, as so this dot is a map actually from Z mod PZ cross G mod PZ to G mod PZ. So, and this is given by, it takes an element in Z mod PZ which is R bar and an element here in G mod P, it is PG here, sorry, this is PG. So an element, say A plus PG, and it maps it to RA plus PG. First of all, we'll show that this is a well-defined what we call this scalar multiplication is a well-defined function. So let R1 bar is equal to R2 bar. So we had to prove so if this is let R1 and R2 bar are equal, be the elements of Z mod PZ. So if this is true, then R1 is congruent to R2 mod P, or R1 is just R2 plus say PM. Now we have to prove R1 bar of A plus PG. This is the multiplication here. We have to prove it is R2 bar A plus PG, but this is same as, by definition of the multiplication, this is same as R1A plus PG, but R1 is same as R2 plus PM times A plus PG. G. Now R2, P, M and A, they are all the elements of Z, I mean the integers, and by distributive law in integers, this is R2A plus PMA plus PG. This is same as, now A being the element of G, PMA is the element of PG. Now knowing the fact A plus G is equal to G if and only if A is in G, let us take this as knowing the fact little g plus capital G is equal to G if and only if this little g is in G. One can note here that this element PMA, this is in PG, so PMA plus PG is same as PG, so this is R2A plus PG, which is same as R2 bar dot A plus PG. So this is a well-defined multiplication. Now let us prove the another vector space axioms. So the first axiom is R1 bar plus R2 bar scalar multiplication with some element of G mod PG, say A plus PG. This is equal to, by definition, this is equal to R1 plus now R1 plus R2 bar is same as R1 plus R2 whole bar by definition of equivalence classes in Z mod PZ, Z mod MZ. So this is same as R1 plus R2 times A plus PG. So this is R1 A plus R2 A plus PG is same as R1 A plus PG plus R2 A plus PG. This is same as R1 bar A plus PG plus R2 bar A plus PG. So in this case we are done. Now for the second item, we have R1 bar dot A plus PG, A1 plus PG plus A2 plus PG, that is same as R1 bar times A1 plus A2 plus PG. This is R1 A1 plus A2 plus PG. On simplifying this, this is R1 A1 plus PG plus R2 R1 A2 of plus PG. So this is same as R1 bar A plus PG plus R1 bar plus R1 times scalar multiplication with A2 plus PG is A1 here. So this is again true. Similarly, for third item, we have R1 bar dot R2 bar PG A plus PG is same as R1 R2 bar of A plus PG. This is R1 R2 of A plus PG. This is same as R1 R2 of A plus PG, which is equal to R1 bar of R2 A plus PG. This is R1 bar R2 bar of A plus PG. And finally, for the fourth item, 1 dot A plus PG, 1 bar. This is equal to A plus PG for all A plus PG in G mod PG. So hence G mod PG has a Z mod PZ vector space structure. Now let us define the free abelian groups. Let us consider the infinite cyclic groups. So if x1 so on xn are infinite cyclic groups, then their direct sum x1 direct sum so on direct sum xn. Let us denote this by f, is called a free abelian group. Is called a free abelian group. With bases in the set x is called little x1 through little xn. More generally, any group which is isomorphic to f is also called an abelian group. Free abelian group. More generally, any group isomorphic to f is called a free abelian group. So one such example is, if we consider these m copies of set of integers, which is same as by notation z1 cross so on cross z. So this is m times So this is the set of all m tuples. Consider this, which is a group of all m tuples say n1 n2 through nm. These are n tuples of integers. Is a free abelian group. Because each z is an infinite scalar group. So here the basis of this free abelian group, so let us mention here 1 basis of Zm is a set, say ei, where this I runs from 1 to m. Here where this ei is an m tuple, is the m tuple having this one at ith place, at ith component, at ith place, and zero zeros elsewhere. So one can note that, so if this is the example of a free abelian group z to the power m, then a free abelian group is any group which is isomorphic to some copies of the set of integers. So this is a standard definition. A free abelian group is a group which is isomorphic to the some copies of integers. So let us prove the following proposition. So z, m copies of z is isomorphic to n copies of z if and only if m is equal to n. Now this is true because, so if m is equal to n, then Zm is isomorphic to Zn. There is nothing to prove. On the other hand, if Zm is isomorphic to Zn, we have to prove m is equal to n. Now if suppose an abelian group G and abelian group G is direct sum of So G is direct sum of G1 plus throw plus Gn. Then 2G being the subgroup of G, we have then 2G is direct sum of 2G1 plus so on plus 2Gn. Now 2G being a normal subgroup of G, this quotient makes sense. So G mod 2G is same as G1 direct sum so on direct sum Gn, 2G1 direct sum so on 2Gn. Now since this internal direct sum is same as the external direct sum, so this is same as G1 cross so on cross Gn over 2G1 cross so on cross 2Gn. Using the previous proposition, one can note that this is isomorphic to G1 mod 2G1 cross G2 mod 2G2 cross so on cross Gn mod 2Gn. Now let us substitute. Now suppose G is G is equal to Z to the power n. So in particular, if G is equal to Z power n, then size of G mod 2G, which is size of Zm mod 2Zm, which is size of Z mod 2Z cross so on cross Z mod 2Z. This is m times. So the size of this group is 2 times 2 times up to m times. This is 2 to the power m. Finally, Zm is isomorphic to Zn if and only if their order is preserved. That is, if and only if size of Zm to the Zn to Zm is same as Zn mod 2Zn, which is if and only if 2 power m is same as 2 power m is equal to 2 power n, and which is true if and only if m is equal to n. Hence we are done.